Okay, thank you very much for the invitation. I would like to present some results that we have been doing in order to immobilize the catalyst just by dissolution in some uncommon solvent media. We have been exploring a simple approach where we have the catalyst dissolved in non-conventional media such as water, ionic liquids, and other media. Then we run the reaction. We have a solvent, and then there is a phase separation. You can reuse the catalyst in the reaction media. Here is presented some previous examples that shows, for example, in the case of the sharpless asymmetric dihydroxylation, we explore the water surfactant using membrane nanofiltration, also ionic liquids, and later ionic liquids coupled with carbon supercritical CO2. Also, by nucleophilic biphasic substitution, in which the ionic liquid has the enhancement, because it's also a phase transfer promoter. And here I just would like to mention this example because it's a proof of concept where for an enzymatic reaction we can in fact recover the product by sublimation. So just in this line, more recently, since we explored some new ionic liquids at that time based on the tetra-alkyl dimethylguanidinium that can be easily coupled with different chiral anions, we found that the quinic acid is quite efficient for the asymmetric dehydroxylation, where it is not necessary to use the sharpless chiral ligand, so we just need to use 0.5 mole equivalent of this ionic liquid in the presence of the MIM. Ionic liquid can extract with supercritical CO2, and as you can see here, the reaction was quite well without erosion on the yield or enantiomeric excess, and more important, there is a small leach of the osmium that is very toxic and expensive. So I would like to just to present another example which since we have been studying the CH insertion of diazoacetamides using rhodium that is very expensive. So we found that this CH insertion can be found for some substrates in the presence of water, and because the rhodium tetraacetate is very soluble in water, you can see here the color of the rhodium. So we can easily reuse the catalyst just by extraction the product in ether, and this can be done, was demonstrated for about 10 cycles. But for the chiral version, the existing catalysts are not soluble in water, so we explored the possibility to create another catalyst, and we screen the different amino acids by exchanging the carboxylate of the rhodium. And in fact, we found that the phenylalanine in fact forms a new catalyst, and this catalyst we explored the substrate scope. I just would like to show here the reuse. So for this model substrate, we ran the reaction in water, and then we just extracted the ether, and we had new substrate. And as you can see here, there is no erosion on the E and also in the yield. So I would like now to present another system where we explore the resolution of the secondary alcohols, which is useful in the case where both enantiomers are important. And the method we explore, you don't use any post-chemical transformation or chromatography, and you can reuse the system, and it's based on using the enzyme that is suspended in ionic liquid and fatty ester or PEG, and also then you use one ionic acylating agent, or the solvent acts as an acylating agent. We just get the two products by extraction and distillation. And the first example we explored was presented in 2007, where you use one ionic liquid and one ionic acylating agent that we developed, And this system is demonstrated here in this scheme, where we have the enzyme that is suspended in the reaction media. And until now, we explore these 3 reaction media. And with appropriate acylating agent that is not volatile. So we add under vacuum, because the vacuum is useful because it removes the ethanol from the reaction media and makes the process more less reversible. So we add the alcohol, and then the enzyme does the acylation, leaves the other alcohol out, so we can remove by extraction or distillation. And then the alcohol that is attached to the acylating agent, we add again the ethanol, and in the second step gives back the other alcohol that can give can be again removed by extraction or distillation. We demonstrated for two systems in the past, and more recently we also explored to use the PEG carboxylates as a reaction media. And I just show here some examples, in special this last one that in fact these 3 compounds are quite useful from pharmaceutical point of view. And here you can see that we scale up to 5 grams. Just by distillation, we have the 2 enantiomers in moderate enantiomeric excess and yield. So I just would like to complete more or less this approach and to spend some time with this molecule, which is the HMF. The HMF is a compound that can be prepared from carbohydrates. And the HMF has been considered in the future an important building block because it is derived from biomass. And it has been quite important the last years. And you can see here several quite recent reviews, especially this review from Vries, that is very complete. And the main reason why it has been attracting quite interest is because from HMF you can prepare several building blocks. These 4 building blocks may be considered as a substitute to the existing phthalate monomers, and also can prepare different molecules including 2,5-dimethylfuran, and this one that can probably be a biofuel. There is the preparation of HMF is usually done from glucose or fructose that can be prepared from different biopolymers, and a different catalyst has been explored. The glucose is much less reactive, especially metal catalyst. The chromium is very useful is unique for the glucose, and different solvents has been explored, such as the MSO and ionic liquids. But there is several issues regarding with the isolation. One is because HMF is very soluble in aqueous media and polar solvents, has low vapor pressure, low melting point, and is thermal and chemical unstable. So this complicates the isolation, namely by solvent extraction, distillation, or crystallization. So we explore an approach where, in fact, what we do is we try to isolate HMF by precipitation of the reaction media. And we explore different salts that may dissolve the fructose and helps the reaction. So we tested different ammonium salts, and in fact, the tetraethylammonium bromide works quite well. In 15 minutes, gives 91% yield using amber list, and in the presence of 10% weight by weight of water. Here is just presented the overall scheme of the process, where we have the tetraethylammonium bromide at 100 degrees that allows the dissolution of carbohydrate and also promotes the hydration. In the presence of 10% water is absolutely essential to suppress the amines formation. And in the presence of amberlist as a catalyst, we just do the isolation by simple crystallization of the solvent using ethanol and ethyl acetate. In the next slide, which is a quite busy slide, but shows some of the main results under batch conditions. So if you use more diluted reaction media. In fact, the reaction is quantitative, and this is very important. It's almost pure HMF. And if you use more concentrated, the yield is a little lower. But you can also use, you did 6 cycles, and you have an overall yield of 94% and 99% purity. The reaction, the process can also be done in continuous operation. And we extended also for other carbohydrates, but we didn't explore in detail the conditions. So in this case, just use chromium. And since the process is quite robust, we also explore this for the teaching laboratory that we published in Chemical Education in 2013. And in fact, last year, we got a message from a college in US that they are using this method in the teaching laboratory, where you just build a simple reactor in the glass blower, and here you can see the reaction. The reaction comes, the reaction media comes, and then you can see that it works by increasing the column. Just use our method. In this case, use sulfuric acid, and the students got this average yield and purity. But since it's more important to prepare HMF from glucose, so we explore another approach by taking advantage of our process for isolation for a reaction, where you use glucose in the presence of sweet zyme, that is a very well-known enzyme that does the isomerization between glucose and fructose, gives 1-to-1 mixture. And if you can do this isomerization in the reaction medium, then do the dehydration, you get the product. So there are some important aspects for this transformation. The first is the enzymatic isomerization through glucose to fructose needs to occur in the same reaction media as for the hydration to HMF. And it's important that the remaining glucose is stable under the condition where the reaction occurs. And also we should recover the reaction media into the glucose for the next enzymatic step. So in this slide, you can see the whole process, where in red is the isomerization, and here is the reaction, and here is just the isolation from after the reaction. So we did the reaction in 10 gram scale, where he added in the first cycle 10 grams of glucose, and then because there is isomerization in the second and the other steps, we had cycles, we had just 5 grams of glucose. And you can see here is the isolated HMF. You can see that is almost stable for all the steps. Only we can see here the amount of glucose with the cycle, so before the hydration. So this means that the enzyme is lost some activity at least after the 6th cycle. So in the next slide, we can see more or less the overall process. So for the 8 cycles, we got about 87 overall yield in very high purity, in which the enzyme, the tetrathilammonium bromide, can be reused. There is no chromatography, no filtration. So we just isolate the product by filtration, precipitation, and organic solvent evaporation. So since we have the HMF, we also explored to transform the HMF to 2 building blocks via Cannizzaro reaction. These 2 building blocks, the diol and the acid, they are considered quite promising, mainly for polymer as monomers. And because the Cannizzaro reaction is not very useful from the synthetic point of view, because you have 2 molecules, in this case, if you could perform the Cannizzaro and isolate the product, so we explore different conditions, and in fact using 0.9 equivalents of sodium hydroxide in water, and we managed to isolate the two molecules just by selective crystallization ethyl acetate, and we scaled up to now to 12 grams, and of course you can reuse the solvent crystallization. So this process seems quite useful to scale up, and in this case, you don't have any added oxidating or reducing agent, since the canisaro gives the two products. So here is just the overall overview of the process. We're starting from glucose, using tetraethylammonium bromide, and the sweet sign does the isomerization. Then the dehydration using wet tetraethylammonium bromide, then the canisaro. In fact, we have managed to get the two building blocks without any chromatography, and this is the overall heat in quite high purity. So because we prepared some derivatives of HMF, and we just did a preliminary study in order to provide some guidelines about the toxicity of some of these potential building blocks. Here is just a representation of the different molecules that we prepared, and we tested the viability to human skin fibroblast cells that mimics the human healthy tissue. And we compare with the known compounds like furfural alcohol, and also luvulinic acid, which the toxicity is very well known. So these are not a problem to use these compounds. So here you just can see that we change the hydroxyl to chloride, the bisaldehyde. This can be another building block. And also here are just some esters. And here you have the diol and the alcohol and the acid and the decarboxylic acid. This is also considered as a biofuel. So in this slide, we can see just by colors what were the preliminary results, and in fact, by considering the viability and also the reactive organic species formations, we can say from this preliminary study that in fact the bis-dialdehyde seems quite toxic, but the HMF looks okay, and also the decarboxylic acid and the alcohol and the acid. So this appears quite promising building blocks. So just to conclude, the system that we explored shows that using different reaction media and catalysts that are just dissolving reaction media, and doing just simple separation process, we can isolate the product and reuse the catalyst. It seems quite simple and robust system. So I would like to acknowledge the collaborators that were involved, and the names were in each of the published paper. And here is just the current team, and in blue are the members that were involved in this project. And also I'd like to acknowledge the financial support as well, the ACS Green Camps Institute. And thank you very much for your attention.
All right, do we have any questions for the doctor? Anybody? Any questions?
So I'm interested in your, put the enzyme and acid together. So does the acid catalysis will, decompose or, deaggregate the enzyme, the activate, the performance in, transformation in the first step?
So in which reaction? Sorry, I didn't.
You combine the enzyme and the acid, right? From the glucose to HMF, right?
Yeah.
So my question is, the acid, catalysis will decompose or, degrade the, enzyme.
Yeah. Here I didn't have time to explain in detail, but here in red is the process for the isomerization. And in fact, we found that it's absolutely crucial that you have 1:1 of tetraethylammonium bromide and water. And then we remove the enzyme by filtration, and then we have the catalyst for the second step that is in blue. So in fact, each cycle corresponds to two different independent reactions.
I understand. Thank you.